Welcome back everyone. In the last class, we were looking at the definitions of different type of responses that are present for a system. We looked at natural response, we looked at steady state response, we also looked at transient response, and also forced response. And finally, I was talking about frequency response. So, in frequency response, we give a sinusoidal input to an LTI system, and we have seen that the output of the system would be of this form, where basically the magnitude changes to this value and there is a phase change, the frequency remaining the same as was given as the input to the system. And we also say that okay, in that case what we can do is we can change the frequency from 0 to some maybe 10 kilohertz or some value bigger number. We can sweep through different frequency values and we can get a plot where we will have in the x axis omega and in the y axis magnitude, and in the other case omega and in the y axis we can have phase angle. This is what we refer to as Bode plot. Now, in case of Bode plot, there is a slight change in the plot. Now, instead of actually going ahead and plotting the magnitude, we generally plot 10 log of mod of g j omega, and this is known as the dB scale. So, the magnitude is written in dB, 20 log magnitude of g j omega. So, today what we are going to do is we are going to learn how to draw these plots approximately. We do not need an exact Bode plot, we just need an approximate Bode plot to see how does the system behave. Okay? Because if you have to draw a actual Bode plot, you can just, it is just a function of omega, magnitude and phase is a function of omega, you can always write down a code and get the plot. So, we will just look at the approximate Bode plot of a system or of a transfer function. First, let us assume that the system has real poles and zeros. I am giving this assumption just so that I can easily explain what I am trying to say, and then I will remove this assumption. So, if it has real poles and zeros, the transfer function of the system, a general form of the system would look something like that. Here z1, z2, zm are all real numbers, p1, p2 to pn2 are real numbers. Here n1 can be a negative integer or a positive integer. So, if it is a negative integer, then we have a this s to the power n1 term is actually in the numerator, and if it is a positive integer, it is at the denominator. Now, suppose I want to draw the Bode plot for this. So, what will I have to do is I will have to check what is g j omega, because at the end of the day Bode plot is defined by the magnitude of g j omega and the phase of g j omega. So, here is g j omega, the transfer function, in place of s I am putting j omega. Now, what we can do is we can take out these constants z1, z2, zm out and p1, p2, pn out in this form, and we get this nice looking form here. Okay. We write it down in this form because it will help us in drawing the Bode plot. So, you can take it to this form, and here notice that these terms here are constants. Okay. So, what I can do is I can replace it by some constant number, say q, some constant value, and then rest other terms are all dependent on omega. So, this is what our g j omega looks like. Now, let us try to see what will be the magnitude. Remember, in Bode plot the magnitude is 20 log of mod of g j omega. Okay. You can always plot g j omega also, but the definition of Bode plot says that in the y axis the magnitude has to be in dB scale. Okay. Because there may be large variations in magnitude. So, in logarithmic scale in a dB scale we can capture those variations, that is why we plot the magnitude plot in dB scale. Okay, so let us go ahead and see what is 20 log of g j omega. So, 20 log of g j omega is nothing but 20 log q plus 20 log of the magnitude of this, which is magnitude of 1 plus j omega by z1, similarly plus 20 log of 1 plus j omega by z2 and so on. And in the denominator term we have j omega. So, 20 log of mod of j omega, and this is whole to the power of n1, j omega to the power of n1, and since it is in the numerator it will go up. So, we will have a negative number there. So, this is the negative number, this n1 can be taken to the front. So, we will have this term, and then again due to the poles we will have these terms, but all in negative because they were in the denominator. Similarly, we can also find for phase. So, the phase angle corresponding to q, what will be the phase angle? Tan inverse of 0 by q, right, because q is a constant real number. So, the imaginary part is 0. So, you have tan inverse of 0 by q, which is equal to 0. So, that is why q is not actually adding any phase, the only terms which are adding phase are these terms, and directly you see I can directly write tan inverse of omega by z1. I do not have to think what is here. Okay, that is the reason actually we went to these forms, because it is easier to write down the phase angles. Okay. Similarly, since we are using tan inverse, so the denominators will have negative terms. So, they show up as negative terms here. Now, what is good thing to notice here is that if you know how does 20 log of q behave, how does 20 log of 1 plus j omega by z1 behave, each of these terms behave, if you know each of these terms, then you just have to plot them and add them up. So, when I say how does they behave, I mean when omega is varied from say 0 to some number. Okay. So, then how does each of these terms behave? If you know that, then you can easily add the plot corresponding to each of these, and that will give you the combined magnitude plot. So, these factors are essential, that is the reason these factors are essential. Now, I will remove the assumption. The assumption was that the poles and zeros are real. Now, what I do is that suppose the poles and zeros are not real, they are mixed, basically they are real as well and as well as complex. So, in that case you see this part corresponds to say the real part of the poles, and these, suppose I have just shown you one term, I can keep on adding more terms here as well, but just for simplicity's sake I am just taking one term. Say the top term we have complex zeros at the solution of this polynomial, and then we have complex poles at the solution of this polynomial. Okay. Now, these terms can also be rewritten again like the previous case. Again, in place of s we will put j omega, you put j omega everywhere, then you take out these constant terms z1. Now, from here we will take out this term omega 1 square, and from here we will take out this omega 2 square, and then we will have this nice looking form. Now, you might be thinking why am I taking a square here? This is just, you will see that soon when we will go into time domain analysis, you will find that I mean this is some standard form that we are choosing, and at that time I will maybe recollect the reason, you will see why we were using this, because it actually gives you a nice looking expression, that is it I think. I mean there is nothing special about it, just that we do not want to use root of omega 1 and all those terms. So, hence we just write it like this. Now, you see when I take out omega 1 square, this is the terms that you get, and here this two terms, this entire term, these are all constants. Again I can just take out all the constants together and I can define q as this. Okay. Then what am I left with is this expression. This is a similar looking expression that I have just now talked about, this part of the expression, and the green part you can see is this. Now, here omega by omega 1 I am defining as u1, omega by omega 2 is defined as u2. Okay. Do not get confused here, omega 1 is a known number, it is a part of the transfer function itself, whereas the term omega here is the one that we are sweeping. So, from omega is being replaced from 0 to some whatever number, you are changing, sweeping the frequency, okay, and this expression gets evaluated at that point. Now, here this u1 is this and u2 is this. This is so called normalized frequency. So, now from here you can see for this term the magnitude term will come out to be this. This is straightforward, the magnitude term would be this and the phase term would be this, right, because this is nothing but 1 minus u1 square plus 2 zeta 1 u1 j. So, you can easily write down the magnitude and the phase. Similarly, for the bottom part this will be the phase and magnitude. The negative term will come because they are the bottom. So, when you take a log they will go up. Okay. Now, you see, so basically again going back, what is this basically? So, if I have to find out, if I just go back a few slides here, you can see when I had to find out 20 log of g j omega, which is basically the magnitude in dB scale, I was looking at these factors, each of these factors, right, each of these factors I was looking at and then I was just adding them. Similarly, when we found phase, we just looked at each of these factors and then we were adding them. So, I should know how these factors behave and that is what we are going to look into now. So, if you look at the expression, there are these 7 essential or fundamental factors that came out in the transfer functions. One was a constant which we called q, one can be a 0 at the origin. So, suppose the transfer function is s, then you will have a s, say s by s plus 1, then you have a 0 at the origin. If the transfer function is say something like this, then you have a pole at the origin, then you can have a 0 only 0. So, maybe something like this. Okay. In this case you have a 0 0 which will be of the form 1 plus j omega by z. Then you can have a pole term 1 plus j omega by p, these are real poles and real zeros, and finally we can have complex zeros and complex poles. Okay. So, these are the factors. So, if I know how each of these factors behave, if my location of 0 is different, I just have to replace z by a different number, then I can find out what the Bode plot will look like. We will take examples of course later, but first what we will do is we will take each of these factors and see how they behave as omega is changed. Of course, we will look at it approximately. One more thing that we do is we call 1 by z here as t, we rewrite the expression 1 plus j omega by z as 1 plus j omega t and 1 by 1 plus j omega p by p as 1 plus j omega t. Okay. Again, if you want you can always keep it in this form also, but I mean I am just doing that so that it is similar to what it is written in the books, so that it is easier for you to follow, but I mean if you want you can always keep it in like this form, it is just a matter of convention. Okay, now let us look at each of these factors. So, the first factor was q. Now, if your transfer function is just q, then what is the magnitude? 20 log of q, and it does not even depend on omega, right. So, for all values of omega the magnitude will be 20 log of q, and in case of Bode plot, as I had already said, we are varying omega, okay, and the scale that we are using is a logarithmic scale, and that is why you can see that I am plotting this Bode plot in a semi log paper here figure. So, where this is 10 to the power minus 1, this is 1, this is 10. So, for each bigger division there is a decade increase in the frequency, whereas the y axis here is in dB scale. Okay. So, this is minus 10 dB, this is minus 10 dB, this is 0 dB, this is 10 dB, this is 20 dB, whereas in case of phase we are writing the y axis in degree scale, and again the x axis remains as it is in frequency omega, but in a semi log paper or a semi log figure we are drawing this. Okay. So, now if it is 20 log of q, that means you notice that for every frequency here the value of magnitude is 20 log of q, which means that the magnitude plot for q, just q, will look something like this. Say this is the point which is 20 log of q. It can be in the bottom also, it depends upon the value of q of course. Similarly, if we look at phase, what is the phase? Phase here is tan inverse of 0 by q, because q is nothing but q plus j 0. So, we get tan inverse of 0 by q, which is 0 degree. Okay. So, this will be our plot. As we go ahead, we have g j omega equal to 1 by j omega. You can again find out the magnitude. This is the second factor, 1 by s, 1 by s will get replaced by 1 by j omega. The magnitude will be 20 log of magnitude of 1 by j omega, which is nothing but minus 20 log of omega. And notice here, so here it is a function of omega, so no longer it is a constant. So, as omega changes, the magnitude changes. So, how does it change? See, at omega equal to 1, this value will become 0. At omega equal to 0.1, so we will have minus 20 log of 0.1. So, we will have plus 20, you see, plus 20, and then at omega equal to 10, we will have minus 20. Right. So, that means that every decade, this is called decade, right, because this is 10 times, it is decreasing 10 times. So, this is 0.1, this is increasing by 10 times 10. So, every decade there is a minus 20 dB drop. Hence, we will say that in this case the magnitude plot is a minus 20 dB per decade line passing through omega equal to 1 at 0 dB. Okay. So, if supposedly instead of 1 by j omega it was 10 by j omega, say, just for an example, if the transfer function g j omega came out to be this, in that case our magnitude would be 20 log of g j omega, which will be equal to 20 log of 10 minus 20 log of j omega magnitude. Now, for this part you already know it is a minus 20 dB per decade line, but 20 log of 10 is added to it, which is, what is 20 log of 10? That will be 20. So, which means in that case your line will be shifted up. Okay. We will take more examples. So, it will be shifted up by 20 dB. So, we will take more examples later, but for now let us focus on these important elementary factors. Okay. So, what about phase? So, in case of phase it is minus tan inverse of omega by 0, minus is coming because it is a pole that we are talking about here. So, minus tan inverse of omega 0 is minus 90. So, that means for every frequency it is minus 90. So, this will be your phase plot. So, if that is for 1 by j omega, what will be for j omega? J omega, it will be basically 20 log of omega, that means it will be a plus 20 dB per decade line. So, for 1 by j omega it was minus 20 dB per decade line, for plus j omega it will be plus 20 dB per decade line. And the angle in case of 1 by j omega it was minus 90 degree for all frequencies, now it is plus 90 degree for all frequencies. So, we are done with 3 factors. Now, we will look at the next one. So, suppose you have a pole only. So, suppose G s equal to 1 by s or something like that. Okay. So, then you can write your factor will be g j omega equal to 1 by j omega t. So, let us see what will be the magnitude. The magnitude would be minus 20 log of root over of 1 plus omega square by t square. So, the magnitude of this basically I am trying to say. So, that will be the magnitude, and you see I can take out the root. So, this will be the magnitude. Now, remember in the beginning itself I said that we are not trying to draw a exact Bode plot, okay, because if you want to draw a exact Bode plot, what we can do is that I can change the value of omega for different values, I can find out what the magnitude is and then do a simple plot, which all of us know how to do the plot for a function, right. You change the independent variable and you find out the magnitude and you do the plot. That is not what we are looking for here. We are actually trying to draw the approximate Bode plot. Now, what is the approximate Bode plot? Here is the approximation. So, suppose omega is much lesser than 1 by t. Remember, what is 1 by t? 1 by t is p. So, if the frequency omega is much less than the pole, okay, in that case, so p in this case, so this was j omega by p, remember. So, omega is much lesser than p. If the frequency that you are applying is much lesser than the pole, then what will happen? So, in this means that omega t will be much less than 1, right. And if omega t is much less than 1, then I can actually go ahead and neglect this term. So, I will be left with minus 10 log of 1, which is 0. So, again approximation, we are doing an approximation here. Now, what about if omega is much greater than 1 by t, which means omega is much greater than the pole that is present. So, in that case this 1 I can neglect, right. So, in that case you will have minus 10 log omega square t square. So, we are left with minus 20 log of omega t. What will happen at omega equal to 1 by t? So, again at omega equal to 1 by t you can do an approximation with this itself. So, here omega will be replaced by 1 by t. So, we are left with 0 dB. And what will happen at omega equal to 10 by t? Again here you can replace 10 by t. So, if I replace 10 by t, so I am left with minus 20 log of 10, which is nothing but minus 20, and at omega equal to 100 by t it becomes minus 40. So, you can see that at 1 by t it is 0 dB, at 10 by t there is a minus 20 dB, at 100 by t it is at minus 40 dB, which means every decade there is a minus 20 dB drop. I mean minus 20 dB slope is there. So, the line is a minus 20 dB per decade line. So, for every decade there will be a minus 20 dB drop, whereas before this point everything will be 0 dB. So, at omega less than equal to 1 by t we will have a 0 dB per decade line, and at omega greater than equal to 1 by t we will have a minus 20 dB per decade line. So, if I have to draw this, so what I can do is I can say that this is suppose 1 by t, this is 0.1 by t, this is 10 by t. So, remember at omega equal to 1 by t it is a 0 dB line. Okay. So, and then from 1 by t to there will be a drop like this. Okay. So, you can see this will be the plot, because up to 1 by t this is a 0 dB per decade line, which is this, and then from omega greater than 1 by t we have a minus 20 dB per decade line. Here it is 0, at 10 by t we have minus 20. So, at 100 by t we will have minus 40. So, this line will keep on going. Fine. What about the phase? So, the phase in this case is phi equal to minus tan inverse of omega t. Now, again we can go for, if omega t is much lesser than 1, we can actually go ahead and say that this is minus tan inverse of 0. So, this becomes 0 degree. If it is much higher than 1, then we can say that this is something like infinity. In that case, these are again approximations. So, minus tan inverse of infinity is minus 90 degree. At omega equal to 0.1 t, 0.1 by t we will have approximately 5.71 degree, which we are approximating as 0 degree. At omega equal to 1 by t we have minus 45 degree, at omega equal to 10 by t we have minus 90 degree. So, as a whole if you take everything together, so what is happening? At omega less than 0.1 t we are at phi equal to 0 degree, at omega greater than 10 by t we are at minus 90 degree, and between 0.1 by t to 10 by t there is a minus 45 degree per decade line. Okay, because you see at 0.1 by 2 we are at 0 degree, at 1 by t we are at minus 45 degree, at 10 by t we are at minus 90 degree. So, that means there is a minus 45 degree drop every decade. So, hence there is a minus 45 degree per decade line, but after 10 by 2 it is minus 90 degree only. See, at infinity also we are at minus 90 degree. So, after 10 by 2 it is at minus 90 degree, whereas before 1 by t it is at 0 degree. So, as a whole this is how my plot will look like. So, if this is 1 by t, go back 1 decade 0.1 by t and go forward 1 decade 10 by t. So, we will have from this point to this point. So, we will have to go from 0 degree to 90 degree. So, this line better be a minus 45 degree per decade line. Okay. So, if I take this factor, then the magnitude plot and the phase plot, complete magnitude and the phase plot will look like this. So, if you have a if you have a pole, then that pole will lead to a magnitude plot of this form and a phase plot of this form. What about a 0? Just the opposite, right? So, for a 0, instead of a minus 20 dB per decade line, you will have a plus 20 dB per decade line now. And for the phase, instead of it going from along this direction to minus 90 degree, now it will go up to minus 90 degree. This will be a plus 45 degree per decade line, because zeros and poles, these are basically sign change operations only as far as magnitude and phase is concerned. Now comes the final factor, the quadratic factor, the one that led to complex poles and complex zeros. So, this is the one leading to complex poles. Remember, u is equal to omega by omega n in this case. Okay. This is u is normalized frequency. So, if in terms of u, magnitude will come out to be this, which is direct, it is just direct, this is a complex number, you can find out the magnitude, this will be the magnitude, and phi will be this. Remember, this is the definition of u. Okay. In the other cases we were varying with omega, in this case we are varying with u. Actually that also means that we are varying omega only, because omega n is a constant. So, if you vary u, you are varying omega also. Okay. So, just keep in mind that omega u is not the frequency, okay. It is normalized frequency. Let us see what happens. So, if u is quite lesser than 1, which means omega must be less than, is far less than omega n, then what we can do is we can assume that these are smaller numbers, and then we have minus 10 log of 1. Now, of course, you might be thinking, what about this zeta? Zeta can be a big number, right. So, we will see that the value of zeta is generally between 0 to 1. So, we will see that later. However, I mean in general, since we are doing approximations, you can consider this to be 1 for the time being, and you will see what is the effect of zeta soon. I will show you with the plot. Okay. So, in that case, this is what we get. So, if omega is much greater than omega and u is quite high, in that case the magnitude will come out to be minus 20 log of u square. So, in that case you will get minus 40 log of omega by omega n. If omega equal to omega n or u equal to 1, in that case you will get 0 dB, and then, so basically here I am replacing u equal to 1 in this case. So, you will get 0 dB. We go ahead, omega equal to 10 omega n. So, this becomes 10. So, minus 40 log of 10, minus 40 log of 10 is minus 40. Then omega equal to 100 omega n, that means u is 100. In this case from here you get minus 80 dB. Again remember, we are just doing certain approximations here, okay. These are not the exact values, okay. So, you can see that for omega less than equal to omega n, we have a 0 dB per decade line, whereas for omega greater than equal to omega n, we have a minus 40 dB per decade line. Just think about it for a second, okay. So, when we had j of omega 1 by 1 plus j omega t, what was our magnitude plot like? So, magnitude plot was that if omega is less than equal to 1 by t, then we have a 0 dB per decade line, and if omega was greater than 1 by t, we had a minus 20 dB per decade line. Now, think about it if you square it. So, then if you square it, then this becomes minus 40, right, but square is like a quadratic term. So, this is also a quadratic term. So, that is what essentially is happening here, okay. Because of that quadratic term, this minus 20 is becoming minus 40, okay. Of course, I have not shown you what is the effect of zeta here, because this entire analysis nowhere zeta is coming into the picture, you can see that, because I am approximating that that is a small number, okay, from 0 to 1. Again, of course, I should again stop here and tell you that, see, zeta has a very important meaning, okay, which we will get to know what is the meaning sooner, in the next few lectures only. But for now, we just assume that it is from 0 to 1, its physical meaning will soon be clear to you. Okay, so this is the line we get. Now, it is a minus 40 dB per decade line from omega n here, okay. The other case, this frequency was 1 by t, okay, remember this is omega n in this case. Similarly, if you go for the angle or the phase, then you will have similar kind of thing. So, in case of a pole, if you remember, it was 0 degree, then minus 45 degree per decade line, and then it stopped at minus 90 degree. This is how it was behaving, right. Now, in this case, how it is behaving? Because again the factor of 2, so it is starting at 0 degree. So, this is omega n, you go back 1 decade, you go forward 1 decade. So, here instead of minus 90 it is 2 times, so minus 180, here it is 0, then you draw a line, that means it is a minus 45 degree per decade line. So, this is your complete plot. Now, this is the case for the zeros in the complex, if you have complex zeros. So, for complex poles you had already seen. So, these were minus 40 dB per decade lines, the magnitude, and then you had minus 90 degree per decade line for the phase. So, in case of zeros, it will just be the opposite, the signs will change. So, all these plots you might have seen that there is always this one point where there is a change, right. That point where there is a change in slope. What is that change? The change in slope. The point where there is a change in slope of the magnitude plot, that point is called corner frequency. And if you go back you will see that the corner frequency in this case was 1 by t. You see, this was the 0 case. So, the corner frequency is nothing but the 0, because 1 by t is nothing but z, right. So, in the other case, in case of poles, let us see, in case of poles the corner frequency is p, okay. The pole is the corner frequency. So, at the corner frequency at the pole location there is a change in the slope. Similarly, for the other cases, for the case of quadratic case at omega n square. So, in case of the quadratic factor at omega n you will have the corner frequency here, okay, not at poles or zeros, because those are complex numbers, right, because these are complex poles and complex zeros. So, we will look at the corner frequency, in this case is the omega n. Okay, what was omega n? Omega 1 n was this factor. If you remember, this was how it was looking, right. This was the omega n factor, okay, the constant number, the constant that you had. This also has a meaning, this also has a very important meaning, we will get to all those soon. Great. So, now that we know each of the factors how they behave, so let me just show you something. So, I will now show you that how does this sigma affect it, okay. So, you will see that if I plot, this is for minus 10 log of 10 1 minus u square. So, this is the so this is what I am plotting, okay, this is what I am plotting. So, if I plot this as u varies, how does variation of sigma change the plot? We are looking at that. Forget about the code, I mean the code is not that important, you can look it up always. Let us look at the plot. So, this is how it looks like, okay. So, this plot you can see that it is sigma is being varied from 0.1 to 1, and for different values of sigma there is some kind of a bump, right, at 10 to the power of 0 here or at 1 here, okay. Now, what is this? This is u. So, 1 means what? U equal to 1 means what? Omega equal to omega n. So, this is the corner frequency, remember. So, this is the corner frequency, and what is important here to note is that you see, if I just take a line here. So, you see up to the corner frequency this will be one line if I do an approximation, and then okay. So, here is the other line will be something like this, and you see this is a minus 40 dB line, you see minus 40 dB per decade line. So, it is 0 0 0 at the corner frequency there is a change in the slope, and we are getting to minus 40 dB at u equal to 10, which is omega equal to 10 omega n. So, after a decade there is a, so from 0 dB to minus 40 dB it is going. So, from slope perspective you see this zeta is not affecting that much. Similar is the case for phase also, you can see in the phase also it is going from 0, and then so from 0 there will be a drop, there will be a minus 90 degree per decade drop, and then you reach minus 180 degree. So, if you think of this from slope perspective there is not much change actually, but of course, when you look at it from if you want to exactly plot the Bode plot then there will be differences, okay. So, I will end here itself, and then in the next lecture we will see how does these things help us. Thank you.